cell which has just got a single nucleus instead of having two nuclei like Reed Sternberg cell. And you can see the level of variation over here. And at the bottom, there is yet another type of cell, and you can see corresponding images and the variation in this case. Okay? So try to put yourself into pathologist's shoes and say, this is something that they say initially. And they have to figure out where one or more of those types of Hodgkin's lymphoma cells are. So it's equivalent to finding a needle in a haystack. And this is, let me clarify, this is one of the high resolution images. It's not a low resolution image. This was acquired at 20x resolution. So just to find those owl cell type of cells, sometimes they have to go as high as like say 60x or 100x. So you can see like how tedious, cumbersome, and time consuming this whole process is. And just think about it this way, right? Pathologists, just like you and me, they're human beings too. So let's say somebody gets a case at 4:30 in the afternoon. The person has worked throughout the day. I can almost virtually guarantee you that he or she is not going to be at their highest level of alertness. It's quite possible to miss something in that case. So that's where the errors occur. And if they don't find, say, a Hodgkin's lymphoma in this case, they might lose the opportunity to find it in stage 1 or stage 2, and the disease might progress to stage 3 or stage 4, where it might even get fatal. Just to give you guys an idea, this is higher magnification, 80x, and there's a hint that there are Reed Sternberg cells over here, but it's very hard for even an experienced pathologist to just quickly look at it and identify where those are. They have to look through it to figure out that, hey, there are 2 Reed Sternberg cells. There is actually a single Hodgkin cell as well. And now you can see the amount of difficulty in the manual process for any pathologist to figure out whether somebody has these cells or not. I'll show you another example. You can see in the middle that there is an odd-looking cell. It's called lacunar cell. That's a hint. But this sample also has another lacunar cell. And it's hard to figure out where it is until I put the labels that show that there's one in the middle and there is one on top of it, slightly towards the left. The point I'm trying to make is this is incredibly hard for people to figure out, and that's what sometimes causes to, the misdiagnosis or missing the opportunity to find somebody's disease in early stages. Okay? So that brings us to a question that now we know that this is an important disease. It affects the kids. To diagnose it is incredibly hard. It's a manual process. So can we apply machine learning to this disease and help our fellow pathologists, right? So before we answer that question, let's look at what kind of problem we are trying to solve over here. Right? So if we just look at the traditional image processing methods to figure out if we had to do any kind of feature detection, what are the typical features in this case, and what do they get affected by? So I have listed some of the main ones. Brightness or contrast, no-brainer. It depends on the image calibration. So a pathological lab might have multiple scanners. So even if you have to put the same tissue sample under different scanners, the image that you get would be quite different. And it depends upon how the individual imager or scanner was calibrated when they installed it, or periodically when they tuned it. Okay? So there is variability there depending upon the source of the data. Second point is color or intensity. I already showed you some of the images from H&E or CD15 or CD30, and you could see that over there, the colors look completely different. H&E was more like purple and pink versus the others had blues and deep browns or cyan colors. So that brings another level of variation. In some microscopic cases, what they do is they acquire grayscale images. So instead of getting a color signal, you would just get a grayscale signal with intensity varying between certain numbers. So that's another level of variation that comes into picture. The next three, like size, shape, location, these are easy to get the intuition about. It just depends upon the cell structure or the tissue structure as to where in the image you'll find those cancerous cells, how they would be orientated, like straight up, turn to the right, turn to the left, or even the position. within the entire image, could be anywhere. Right? And then last but not the least is noise. Physically, depending upon whether you use bright field microscopy or fluorescent microscopy using lasers, what happens is light does get reflected, a part of it does get refracted. That creates noise. You get some spurious dots or colors, which you would think that it's part of the tissue, but they are really not. It's part of the noise. So you can see that there are all these issues that affect. But if you were to just remember a couple of slides back when I showed you those owl's eye figures or other things, for a human, just by knowing that, hey, if there is a Reed Sternberg cell, it kind of looks like this, people can figure it out given enough time. So which means that there is a pattern that exists. It's not that there's no pattern, this is just random data. So that's a good sign. Another thing is, but if I ask any one of you or try to do it myself, try to define that pattern mathematically, it will be pretty damn hard. I could probably get double PhD by just doing that, and we'll spend a few years. So maybe not the best use of anybody's time, right? The third one is, when the images come from the microscope, there's no label on it. You'll get fantastic images. You can acquire like hundreds, thousands, millions of those with beautiful looking pictures. If you look at it, you'll be able to figure out that there's a Reed Sternberg cell. But when the image comes to you, they're just the raw image data. There's no label on it. So bulk of the data is unlabeled in this case. And there's a lot of it which is available. Right? But at the same time, we could also leverage the pathologists and ask them to label at least a few of those images. Right? So there is some data which is labeled, which is available. If we look at all four of these factors, the first two lend this problem itself very well to machine learning. This could be a good problem to solve using machine learning. And if I look at number 3 and number 4, this will tell me that this is actually a good problem to solve using deep learning. I could use the unlabeled data and some of the unsupervised feature detection algorithms initially, and then eventually, at the last classification stage, depend on my small amount of labeled data to do the classification. Right? So using this intuition, let's look at what we can do using deep learning. At the bottom, I listed 2 of the most popular algorithms in the deep learning space currently. And at the top, I tried to show you some kind of intuition as to what will happen as part of that deep learning. On the left-hand side, it's just the raw image, bunch of pixels. And as the deep network progresses through multiple layers, what will happen is it will start learning features depending upon all those 8 factors that I listed, and probably a bunch of dozens or even hundreds of other features that I, as a human or other people, would not have been able to discern readily. And eventually, the aim would be that you have this network deep enough so that it's fast to learn and fast to predict, and yet you get high level of accuracy. Now, especially at G, when we do this, our main criteria is accuracy. In case of accuracy, again, with false positives and false negatives, we err on the side of caution. So for us, false negatives, making that 0% is the goal. If we have to get some false positives along the process, we are okay with it. Because with false positive, what will happen is maybe this network will detect a tumor cell, and pathologists would look at it and say, oh, no, that's not a tumor cell, that's okay. So it's a little bit of waste of that person's time. But at least by not having any false negatives, we won't end up missing the opportunity of detecting cancer in an early stage. So that's how we fine-tune our internal networks. We have been using multiple approaches. Stacked autoencoders could be known to some of you guys who have already worked in this area, but it works really well with unsupervised feature learning. What I have on the left-hand side is a basic autoencoder. It shows you that there are inputs, there's a hidden layer, and then there are outputs. And the aim over here is to create the input in the output layer as closely as possible. And the hidden layer could take different forms. It could have less units compared to number of input or output units. It could even have more units compared to input or output units. And depending upon what type of architecture it is, there are variations in the point two, the bullet number 2. Like there is a sparse autoencoders where your hidden layer would be much larger compared to input or output layer, or denoising where it could be smaller or of the same size, or you could just go with plain autoencoders. When it comes to weights between the layers, can be independent weights or tied weights. The idea with the autoencoders over here is that when you use autoencoder to recreate the input, it ends up learning some type of features. It's similar to principal component analysis, but principal component analysis is linear. And because the activation functions that are used over here are completely nonlinear, like log sigmoid or tanh, this has a way of learning even really complex nonlinear transformations. And this part is called as pre-training. You can pre-train these and have a multiple of those where the lower layers learn lower level features, and as they move forward, they start learning higher and higher level features. And finally, stack the pre-trained autoencoders into a network that looks like a typical ANN, artificial neural network. And for the last layer, you can use supervised learning using any of the classifiers like softmax classifier. So the idea is that you use unlabeled data for all the hidden layers and the input layer to learn some features. And in the last layer, you use the supervised learning for final classification. A combination of those is really powerful, provides high level of accuracy and generalization. Another one that we try is deep belief networks. The idea is extremely similar. On the top, what I have shown is a typical restricted Boltzmann machine. You can see that there are only 2 layers. There is a visible layer with V's, and there's a hidden layer with H's. And instead of using the typical gradient descent, in this case, we end up using contrastive divergence algorithm to pre-train the restricted Boltzmann machine. And what I have shown on the lower left-hand side is stacking these restricted Boltzmann machines in multiple layers to learn the features in a hierarchical fashion. And similar to stacked autoencoders, what we do is, for the final layer, we would do the supervised learning and backpropagation for the final classification. Similar to stacked autoencoders, deep belief networks also have very high accuracy. Sometimes they are a little bit hard to train compared to autoencoders do, but it really depends on a case-by-case basis. At GE, what we like to do is we like to have all these algorithms in the tool set and run all the experiments using all the tools that are available in the tool set, because you never know, or you can never predict which solution will turn out to be the better one. And we end up picking up the best solution from our toolbox in the end. So using these basic building blocks, what we do is, I have given you a very high-level overview of our internal deep network. The first 2 steps, if you look at input image or image patches, these are the pre-processing steps. What we do in this case essentially is chop the image up into smaller chunks so that they can be efficiently processed for learning features as well as for prediction. And from intensity quantization through edge detection and image segmentation and shape detection, finally what we do is, these are larger boxes. Internally, they might represent more than 1 step. In many cases, they actually have multiple steps. But the idea is that you normalize the image, then the network learns how to normalize it, then how to detect individual edges, finally understand shapes out of it, and eventually identify an object like a Reed Sternberg cell or a lacunar cell, or just normal cells where it would say, hey, some of these cells are non-cancerous. Now I'm going to show you some of the results. So this is one of the cases. On the left-hand side, you can see in that red circle, that's one of the Hodkin lymphoma cells. And on the right-hand side, this is some of the internal feature detected areas. And we are able to achieve very high level of accuracy in this case. You can see it's very close to almost 100%. The way entire pipeline or the deep network was designed was to make it generic so that the same idea could be applied across other type of cancers, across other type of image segmentation or object recognition type of problems. It's very valuable to the company. I work for GE because GE is in so many other businesses where the same technology is reusable and useful. So what we have is, I'll show you one example where we have been able to expand it very successfully. And this is other type of pathological images. Now here what you see is the cells that are from different organs. And on the left-hand side, it uses different types of stains. So it shows nuclear, cytoplasm, or microtubule, or another set of nuclear. And the same technology was used to provide segmentation. I apologize, these images are compressed together, so it's hard to see the segmentation quickly, but just wanted to give you an idea considering the time limit that I have today. So we have been able to expand it, use it in a generic fashion without many changes. And we are also working on other areas which are not related to just the healthcare part of it. I won't get into some of the details considering time, and I'll open it up for Q&A.
So for cases where you have just a little bit of training data, is it possible to use like the same tricks they use with OCR, like artificially modify that, the positive labels?
Good question. So in case of limited training data, there is another aspect that we use. We call it synthetic data because our data is images. So essentially we add, whenever we have labeled data, we add image transformations like translations, rotations, mirror images to create additional labeled data out of it. And that also helps to increase the amount of data available for the supervised learning. Sure.
You mentioned 99.8% accuracy. How does that compare against human pathologists? What is the average accuracy?
With the best of the pathologists in the morning, and I'll qualify that. You know, when they're really fresh, like they're completely alert, the typical rates are about 97%. And the rates decrease, and this has been proven, and not just for pathologists, for other healthcare professionals too, that the accuracy decreases with the alertness. So towards like end of the shift at 5 o'clock, it goes down to anywhere around 90%.
I guess I'm wondering, I'm sure there are multiple other methodologies today to help the pathologist to, I mean, it's very difficult to manually figure out where the cancer cells are. I'm sure there are blood tests and many other things they're doing simultaneously, right? So I guess I'm trying to understand, in current practices, how important is it to see an image and how important the image is to the pathologist when he or she makes her final decision for that test?
For some type of cancers, like say Hodgkin's lymphoma, is very, very important. There are other types of cancers where you may not even use pathology. You might use a CT scan or MRIs. There are others where you may not even use those. You know, you might just do a blood test and look at, let's say, especially for leukemia. The initial screening is done by using blood tests, and there is a flow cytometry. So it's a completely different technique. So you're absolutely right. You know, there are other types of cancers where you won't use this technique.
So for this cancer, image recognition from a manual image recognition is like 80% of the decision-making process. That's what you're saying.
For Hodgkin's lymphoma, it is one of the main ones. So what they do is, once they make the diagnosis, this is not the end of it. They might run some additional tests to confirm it, because what I showed is like very high-level overview. Hodgkin's lymphoma has about 10 to 12 different subtypes, and they have to run additional tests to figure out what subtype it is, and do the staging to figure out what stage the patient is in before they proceed further.
So now just one question. Are you mostly dealing with the 2D images, or you also process 3D images?
We did that with 2D images, because in this case, unlike say CT reconstruction, where you take the 2D slices and create 3Ds out of it, the pathological images just come at 2D, and they look at those individually. But in case of right. But in case of say CT, we do have internal work going on for 3D images with 3D reconstruction as well.
Given that the human method of detecting cancer cells is inaccurate, do you have problems with your label data being inaccurate, or like having something be labeled as not having a cancer cell that does have a
Very good question. I wouldn't call it completely inaccurate, but typically what happens is if you ask a person like a pathologist to draw just a line around a cell, depending upon the resolution, when they draw the line may be a little off. But sometimes with the machine is able to just compare 2 pixels next to each other. So a machine has slightly higher level of accuracy. But whenever we have that kind of situation where machine did not agree with the pathology by a certain margin, but when when the engineers looked at it and said that, hey, machine looks to be more accurate, we actually reviewed the cases with pathologists to see if we are getting something wrong or if their outline was a little bit approximate. And in most of the cases, they said that a machine is getting it even with a higher precision than what a person can do. So that happens too.
I'm trying to understand how big the problem you're solving. Like, what is the percentage of false negatives that happen through manual recognition today? And what do you think image recognition through this?
So for us, it's a combination. It's detecting the false negatives and as well as speeding up the whole process. Because if you look at what's going on in the industries, there is Affordable Care Act. There's a lot of pressure being put from the society, all of us, to reduce the healthcare costs. And this is one of the area where the existing process is highly manual. So the idea is that if we apply the machine and bring up some of these to the pathologist's attention, saying that, hey, is this a cancer or is this not a cancer? Not only can we reduce the false negatives, we can also speed up the whole process and reduce the costs. So it's a multifaceted solution.
How is this tool, is this built into a GE scanner? Is that already sold to a provider organization?
In future, this is not out yet. In future, this will be part of the software stack that goes with GE scanners.
I have a question. You mentioned, like, besides this image processing, you're using it for other areas as well. So curious where exactly do you using this technology?
We have other types of cancers. There is also a group that's working on the Alzheimer's disease. They are also looking at this. And we have other or modalities like CT, MRI, ultrasound. There are people who are looking at application of this in those two, let's say, for 3D images with 3D reconstruction. For the non-medical one, we have some interest from GE's aviation, where they could use this for looking at, say, faults, mechanical faults or structural faults in, say, aircraft wing or even aircraft engine or other type of parts. And there are similar type of use cases for transportation, as well as oil and gas. So I'm being asked to stop. Time is over, but I'll be outside, so if you guys have more questions, I can address those there. Okay? Thank you very much.